Hey everyone, Thrasher here. We are looking at a topic known as conservation of momentum. So we're going to show where that equation comes from, look at a couple examples, and then we're going to end the video with a couple new definitions, which is all about types of forces. Okay, so first slide. Going over what conservation of momentum means, what it's going over, what it's discussing. We're going to start with our impulse equation. All right, we're going to start right here. So if there's no net force on an object, if we look at our impulse equation, we would plug in 0 for the force. Well, 0 right there multiplied by time, that's obviously going to go to 0. Well, 0 is equal to the change in momentum. I could add this initial momentum to both sides, and I have this, mv naught equals mv, or rewritten, the initial momentum is equal to the final momentum, just because remember P equals mv. So this is saying something pretty simple, really. If there's no net force on an object, its momentum remains constant. Its momentum is conserved. There's that term again. All right, and this is intuitive because if there's no force, there's no acceleration, and if something isn't accelerating, its velocity is not changing. Momentum is based on velocity, so momentum stays the same too. More generally, though, this is not just true for one object. This is true for systems of objects as well. If there's no net force on a system, then the total momentum is conserved. Total momentum conserved in systems. So you could almost think of it like this equation here works for an individual object, but if we go through our reasoning for a whole system, several objects colliding, then the momentum is also conserved in total for all those objects. So let's look at an example. All right, I have here a before the collision, we're looking at collisions, a during, kind of right at the collision, and then afterwards. Okay, so here is the initial time. All right, I have two objects moving towards each other. Let's say this one has a mass of m1, this one has a mass of m2. And this is their velocities, v1 and v2. Maybe these are like the initial velocities, so we could add a little 0 here for initial. And they collide, they crash. Imagine playing billiards, shooting pool. And then they bounce off. They obviously still have their same masses. Now they're going in opposite directions. So now instead of the naught, it's just regular v1, v2. You might also see the symbol prime. It looks like a little apostrophe. Physicists like to use multiple forms of notation. You might see this one too. This just means the final, after the collision. Well, if momentum is conserved, that's what we're looking at. Really what it is saying is that P naught equals P. The initial momentum is the final momentum. Again, using that notation with prime, you might see P equals P prime. Okay, but I'll stick with what I wrote first. That means in the beginning that if I look at the initial momentum of ball 1, that purple one, and I add it to the initial momentum of ball 2, that should equal the final momentum of ball 1 plus the final momentum of ball 2. So I just look at my pieces. I say, here's a piece. Let's write out its momentum. Here's another piece, its momentum. Before the crash and after the crash, the total, the combined momentum stays the same. Well, if I plug in for this purple ball here, that would be like m1 times v1 initial, plus for my greenish yellow ball, that would be m2 v2 initial. Well, that's going to equal m1 v1, or maybe again v1 prime. You might see that symbol. Plus, gotta get back to my blue pen, plus m2 v2 prime. Now, yes, we have to remember that momentum is a vector, so if we said that like to the right is positive, then this one might now have a negative momentum, so you could plug in a negative velocity here, or you could just stick in a negative, but you do have to keep track of that. M2 started off going negative, so you could plug in a negative velocity or put in a negative right here. But really what I want us to focus on is just the equation we wrote. It's all about adding up the momentums in the beginning. They need to equal the momentums in the end. Okay, and then obviously if you're given numbers in a certain problem, you could solve for some of these quantities. This type of collision, where I have two objects that start apart, they collide, they crash into each other, and then they stay apart, they bounce off. This is known as an elastic collision. That is worth knowing. You will hear that terminology. This is an elastic collision. Okay? Things start apart, they bounce off, and they remain apart. Now, during these collisions, some energy is always lost due to like sound or the warping of material, but there is a theoretical type of collision known as a perfectly elastic collision. Now, these don't really exist in real life, but once again, it gives us a way of simplifying certain problems. You might come across something known as a perfectly elastic collision. If they say an object or a set of objects has a perfectly elastic collision, there's no energy loss. All right? And if there's no energy loss before or after, the kinetic energy, the total kinetic energy of the system would also be conserved. You could say that K naught equals K. And you could add up the initial kinetic energy of object 1 plus the initial kinetic energy of object 2 equals the final kinetic energy of object 1 plus the final kinetic energy of object 2. We might see a couple examples of that, but just know it would have to say perfectly elastic. Otherwise, this is not true. This is not always true. Okay? In fact, in real life, it's never true. But in an ideal case where we have something that's known as perfectly elastic, the kinetic energy would stay the same. Anyway, that was one type of an example. Let's look at another type. All right, starts off very similar. Let's say I have some object, M1, and it's being thrown at object M2. But maybe this is like clay, or maybe it's like Play-Doh. So this object is moving, has some velocity v1 initial. It slaps into this ball. It warps, it gets all stuck. And now I have these two things combined. They're moving together with some final velocity v. We can again apply the idea of conservation of momentum. All right, the initial momentum of everything added up is the final. So that would be m1 times v1 initial plus m2 v2 initial. It looks like this thing is at rest, but obviously it doesn't have to be. They stick together. Now it's like one object, one larger object. So I could do m1 plus m2 times that final velocity, m1 plus m2. So here's something you need to recognize. There's not really one mega equation for conservation of momentum, kind of aside from this one. All right? Your job is just to look at things before and after and add up the momentum of the pieces. Okay? So in our last problem, we had these two things that started apart, so separate, and they ended apart, separate. Okay? But I'm still doing the same thing. I'm just adding up the momentums, and if they're now together, they would obviously be moving together with some constant velocity. This type of collision here, where things are sticking together, this is known as an elastic collision. Elastic. Okay, things started apart, they collided, and they ended up now stuck together. Okay, if it's an inelastic collision, these objects are now moving together as one, at least in this example. Okay, so we're going to be getting practice setting up these equations for objects that are colliding. Here's why momentum is so useful, and in fact, you could argue it's more powerful than energy conservation. When we were applying conservation of energy, it was always for one object at a time. But notice, we were just using a conservation equation for multiple objects. I can even include collisions in my conservation of momentum here. Okay, you can't do that easily with energy conservation. Okay, last thing, part B. We have two new types of forces that we have to specify. Forces that are known as internal and forces that are known as external. You might have thought when I introduced this first collision here, wait a second, Thrasher, you said at the very beginning that you're assuming there's zero force. But obviously when there's a collision taking place, there are forces interacting between these two objects. Okay, obviously this purple ball is going to apply a force on the greenish yellow, And by the third law, the greenish yellow is going to apply a force back. So we have to be clear what type of forces we're dealing with. And it again goes back to systems. Systems were important for forces a little bit. They were important for energy. They are also important for momentum. And it's all about whether a force is internal or external. So we say that a force is internal if it's happening within the system. All right? So if my system is just this pink ball here, if this is my system, the only forces that would be internal would be like the atomic forces maybe holding the ball together. When this ball slams into the green ball is applying an outside force, an external force. Its momentum, if my system is the pink ball, would not be conserved because it has some velocity here, and now it has some new velocity. There was some force applied. Force I might draw like this. F. So if my system is just one object, in this case, this system's momentum is not conserved. I had some velocity to the right, some momentum to the right. There was a force. Now its momentum changed. That's why it's important to declare what our systems are going to be. So an external force is one that's outside of our system. An internal force is one that is within the system. Let's say that our system is now this. It is the two objects together. Well, yeah, they collide, but these forces here, there's a force acting on the green ball, there's a force acting on the pink ball. These are now internal forces. All right? Here's my system in the last one. The total momentum is conserved if my system is these two objects because, like, there wasn't some earthquake happening on the outside. Okay, Mr. Thrasher wasn't swatting these two balls away. These red arrows I just drew weren't occurring. Any force that was taking place were internal forces inside the system. So when we're talking about momentum being conserved, the big idea is this one. Momentum is conserved as long as there are no external forces. All right, and that's pretty much always going to be assumed unless it seems a little iffy, or at least or unless a problem says otherwise. We can assume momentum is conserved, but make sure you recognize what your system is. That can be important. And just like for energy, the AP test can sometimes be a bit of a bother trying to trip you up. Last thing I have to say, and we'll talk about this more in class, we have internal, external forces, and we also have conservative and non-conservative forces. These are not the same thing. Okay? The whole idea of energy conservation is if there's no non-conservative forces. All right, for momentum to be conserved, we need no external forces. Okay, a lot of students flip those terms up, but luckily the AP test and my test, usually you don't have to include that in your reasoning, but they are a different thing. Okay, we'll be practicing this in the next week or so. Thank you very much for watching.